All right. Today we're talking about symmetry. We are going to be able to identify graphically some different types of symmetry, but then also be able to not test it so much as prove it algebraically for the different types of symmetry that we have. So we have a couple of types of symmetry, which we did a lot of in geometry for those of you that had me. Thanks. All right, so first we have symmetry about a line. We can call that line symmetry. Line symmetry. And so when I look here, line symmetry happens when we can fold our curve, really, along a line so that the two halves would fold on top of one another. And so here in this first picture, what line are we folding on? X-axis, yeah. So here we could fold that graph in half along the x-axis, and that would be called symmetry with respect to the x-axis, all right, or x-axis symmetry, if you will. Symmetry with respect to the x-axis, because it would fold right on top of itself across that x-axis. So now, what is kind of nice, too, is to think about what happens to the ordered pairs when we do that. So let's pretend here this point is on this graph. This point is the point 4, 2. Now, if that point is on the top half of the curve, it gets reflected across the line, the x-axis. And what's this ordered pair down here then? 4, -2. And so you'll notice that the x stayed the same, but the y becomes the opposite. All right? Now, the second picture here, what would we fold along the y-axis? Yeah, if we were to fold this, it would fold and line up on itself if we folded it along the y-axis. So we call this symmetry with respect to the y-axis, okay? With respect, because it's important. With respect, yeah. So we could. Regards to it, referencing the y-axis, we could say y-axis symmetry. Symmetry across the y-axis. Lots of ways to say it. So with respect is another way to say it. Now, again, just like before, if I had a certain point on there, let's pretend that this is the point 3, 2. Now, if this is the point 3, 2 on the right-hand side of the graph, and it has symmetry, so it gets reflected across the y-axis, what's that new point? -3, 2. So in symmetry with respect to the y-axis, you okay, Scott? Okay. All right. So when we have symmetry with respect to the y-axis, the y stays the same, but the x's are opposite. Interesting. Y-axis symmetry, the y stays the same, but the x's are opposite. In symmetry with respect to the x-axis, the x stays the same, but the y's are opposite. Do you see that? Okay. Okay. Now, we also have, not only do we have line symmetry, or symmetry with respect to the x and y-axis, but we also have point symmetry. Symmetry. And the point that we usually rotate around is the origin. So a graph remains unchanged when rotated about 180 degrees around a point. The origin, for instance. This is an example of a curve that has symmetry with respect to the origin. So what happens here if I have a nice point on my curve, like this point here, we're going to call this the point 2,8. I'm going to call that the point 2,8. So what happens is, I don't know if you remember from geometry, if we wanted to take this point and rotate it 180 degrees about the origin, then do you remember the little robot arms that we used to do? Oh, you sure do. We'd have to go 2 units to the right, and we make this little elbow L. So it goes over 2 and up 8. And then to rotate 180 degrees, we would have to rotate this. There's one up 2 and over 8. That's 90 degrees. And then we could do it again. And now here 2 and then down 8. So we get here. That was 180 degree rotation. Do you remember doing vaguely?
I remember like every guy in my class laughing about that.
Oh yeah, I remember that too.
Yeah.
Oh yeah.
Yeah.
All right. So we have these little rotations. We can rotate that point 180 degrees around the origin, and that point then turns into, it went left 2 and down 8, -2, -8. So when we have symmetry with respect to the origin, the x's become opposite, and the y's become opposite. Opposite x and opposite y's. And that's very important to remember. Symmetry about the origin, everything is opposite. Lots of O's. Okay? All right. So the x-axis and the y-axis are common lines of symmetry, and the origin is a common point of symmetry. And we can use symmetry to help us graph. Now, I will say we have graphing calculators, which can be extremely helpful here. Guys, I know I'm not that interesting, but please pay attention to me and not your computer. Thank you. All right. So we can use this to help us graph, to recognize symmetry. We're not going to do it too much in this class, though. But I need to introduce you just to the different kinds of symmetry because it comes up and can be useful. So we can actually test for symmetry. And if you can remember some very simple pictures like what we started with, then figuring out how to prove it algebraically is pretty nice and pretty easy. We noticed that when we had symmetry with respect to the x-axis, the x stayed the same, but the y values became their opposite. We can use that information to actually prove things have symmetry with respect to the x-axis. For every point xy on the graph, the point x negative y is also on the graph. So what we want to do to prove it is replace the y with the opposite, which would be negative y. And if we do that, we want to see that the equation matches what we started with, okay? Which is kind of interesting. The y-axis, we said that the y stays the same, but the x becomes opposite. And so we can do that same thing for every xy point on the graph. The point, let's see, the x became the opposite, but the y stayed the same. And so to prove algebraically, we're going to replace the x with negative x and work it out and then see, do we get the same thing we started with or not? Okay. For origin, when we look at our origin symmetry here, everything was opposite. The x's turned opposite and the y's turned opposite. So for the origin, any xy point gets rotated and becomes the opposite x and the opposite y, negative x, negative y. And so again, if we wanted to prove it, we would replace x with negative x and y with negative y, and then we'll do the math, clean it up, and see, do we get the same thing we started with, okay? So we're going to do both of those things. So directions, use the graph to determine if the relation is symmetrical to the x-axis, y-axis, or origin, and then confirm algebraically. And I am going to want to see the algebra, ladies and gentlemen. They've given us an equation here. Pretty nice. They've given us a graph. If we just had an equation, could we maybe use our calculator to graph it? Yeah. Absolutely. Okay. Just looking at the picture, what would you say the symmetry is? Y-axis symmetry. And when I'm looking, so y-axis symmetry, that is an excellent guess. I also can verify with a point. So like right here is the point 2, 1. And then on the opposite side, it would be negative 2, 1. So the x value became negative, but the y stayed the same. Great. So we can see that we have some symmetry at the point level. Okay, the y stayed the same. That's a y symmetry. And that helps me figure out what I should do. I'm going to take my equation. The y stayed the same. We think it's y-axis symmetry. The y stays the same. And so what I want to do is, in my equation, I want to replace x with negative x. So I'm going to take my equation, leave the y alone, because that's what my point did. The y stayed the same. But my x became the opposite. So everywhere there's an x, I'm going to replace it very carefully with its opposite. And you'll notice I have to use parentheses. -4 and then negative x quantity squared. So we have to replace the x with the opposite. And now we're going to do the algebra and work it out. Negative x quantity to the 4th. Does it turn positive or negative? Turns positive, yeah? Great. Because we're repeating it 4 times. That goes positive x to the 4th. Here I have a negative 4 times. I have to do my exponent first. Negative x quantity squared becomes x squared. It turns positive. And we notice that what we started with, or what we ended with here, it's all nice and cleaned up, matches what we started with. And so it is symmetry with respect to the y-axis. So that's the proof of it, because what we started with is the same as what we end with. Okay? Here we have another graph. Symmetry with respect to the origin is our guess here. It looks kind of like it. It looks like it's a sort of reflection cross. Let's see if I can find a nice point here. Like here, this looks like the point 3, 2. Bless you. And is that point rotated on the other side? Yeah, right there. I see it. It becomes -3, -2. All right. So looking just at the ordered pair level, it looks like everything is opposite. Okay. So to prove that, to prove origin symmetry, I need to replace the x with negative x and the y with negative y, and then just do the math. What is negative x times negative y? It's xy. All right. And did what we finish equal what we started with? Yeah. Yes. So therefore, symmetry with respect to the origin. Okay. Questions so far? Pretty easy, eh? Oh, so number 3, what are we thinking? What kind of symmetry? X-axis? Yeah, good. Okay, so imagine folding that. Looks like it might be x-axis. Maybe we have a point here. This is the point, what, 1, 2, 3, -3, 4? And that same point is down here, -3, -4. So the x stays the same, but the y becomes the opposite. And that helps me figure out how to prove it. We've got to prove it. Okay. 4. So we are going to do what? How do we prove it? plug in a negative to which x or y?
Y.
Good. So we're going to take the y and we're going to replace it with the opposite because that's the thing that changed. So x plus 3 quantity squared plus, we're opposite y, quantity squared, equals 16. Again, here's the important part. Notation. Notation is the important part. I just need to reiterate, negative y squared means what? Okay, the 2 only affects the y, so it says repeat the y 2 times. The negative is hanging out, and then we repeat the y 2 times, we get negative y squared, okay? If we use parentheses, the quantity negative y squared, what does that mean?
It means to do everything.
Everything, negative y times negative y, everything in parentheses, which then results in positive y squared. Notation is the important part here. For those of you that'll see calculus one day, this is the stuff they mark you off for on the calculus exam. If you write, and if you're lazy and don't use the parentheses, and you write negative y squared, but in your head you knew that it should have been positive, you would lose a point because the math wasn't communicated correctly, all right? So it's just really important that you're paying attention to the notation. Okay, here, nothing changes. X plus, oh, that's supposed to be a 3. Nothing changes there. And then negative y quantity squared becomes positive y squared. Good. And so this, what we end with, does it match what we started with? Yes, it does. So that is our x-axis symmetry. All right. 4 is crazy. 4 is crazy.
Wouldn't it be both?
Oh, both?
Both?
Let's see.
Wait, could it be all 3?
Oh, could it be all 3? Let's see. So I definitely think I see some x-axis symmetry here. Kind of looks like it's going through like negative 3, 3, and negative 3, negative 3. So I definitely see some x-axis symmetry. Y-axis, does it look like it's... Oh, yeah. So y-axis symmetry, is it folded left to right? That looks like it could be. What about origin symmetry? Could it be that as well? Let's see. If I take this point 1, 2, 3, 4, 1, 2, 3, 4, 4, can you rotate the whole picture and it land on top of itself? Yeah. What? Yeah. So that rotational symmetry is there too, rotating around the origin 180 degrees. Yeah, all 3. So tricky. Let's see. So to test for x-axis symmetry, what do we do? The y, yeah. So in x-axis symmetry, the x stays, but the y becomes the opposite. So again, if you think about that, you think about the point, that would be down here for negative 4. So the y became the opposite. So that's what I'm going to do for the x-axis symmetry. So negative y squared minus x squared equals 1. And what is negative y quantity squared? Positive y squared. Okay. So that one checks out. That's exactly what we started with. What do we do for y-axis symmetry? So what stays and what changes? The y stays the same. The x becomes opposite. So the y stays the same, but the x turns opposite. And again, that cleans up. Negative x quantity squared becomes positive x squared. And so that is my y-axis symmetry. Same thing you started with. What do we do for origin? All of them. Yep, origin. Everything is opposite. Opposite x, opposite y. So for the origin symmetry, we're going to do the opposite of y and the opposite of x. And then again, so negative y quantity squared becomes y squared, negative x quantity squared is x squared, and it cleans up to exactly what we started with. So there's our proof for that symmetry. Okay, great. Number 5. What kind of symmetry? None is correct. If you look, here's the point, here's the point 2, 1. And if you were to think about rotating that around, and I would want to see it at -2, -1, but it misses, okay? It does not pass through the origin. That's kind of a clue. Most of the time, if it's an origin symmetry, it's got to pass through the origin. If it doesn't, it's going to miss, okay? Now, that's not always true. This one is none. Could be undefined there. All right, I think that's enough. Is that good enough? Okay, awesome. So even and odd. Even and odd is just one step further. A function is even if it is symmetric with respect to the y-axis. So it's really just the same. It's y-axis symmetry, even. It's like a parabola. It's even, all right? It looks even. It's got an even power, right? X squared, all right? That's why we call it even. And again, if we're talking about symmetry with respect to the y-axis, the y value stays the same, but the x becomes opposite. So algebraically, using function notation, we're going to take our function and we're going to change the x to its opposite. And we should get exactly what we started with, okay? So to check it algebraically, just like we were doing before, we replace the x with its opposite and hope that we get the same thing when we're done. Now, a function is odd if it's symmetric with respect to the origin. I like that they did it that way. Origin, odd, there's lots of O's. Everything is opposite, okay? So algebraically with function notation, we would plug in the opposite x, and we hope to get out an opposite function, like the y should turn out to be opposite. The whole function becomes opposite. So it's a slight difference. It's really the same. So let's see how this works. We want to determine algebraically if the function is even, odd, or neither. Well, we're going to help ourselves out. Ladies and gentlemen, will you please take your calculators and give yourself a helping hand here? And let's take our function, and will you plug x cubed minus x in? And look at the graph. So we're thinking origin? Are we thinking origin? Okay. So by looking at the pack, we think it's origin. So that's our question, symmetry. Oh, odd. So we think it's odd. So we want to know, is it an odd function? Is there symmetry about the origin? So to do that, I'm going to replace my function with my opposite x. So everywhere there's an x, we're going to make it opposite. And then I'm going to do the math and clean it up. What is negative x quantity cubed? It's negative x cubed, yep. And then here we have negative times negative x, so that becomes positive x, okay? And then you'll notice what I can do here. I can actually factor out a negative. If I take out the negative, what's left behind? Cubed minus x. Do you see how I took out the negative? Okay, and so we have, there's the x cubed minus x. That's what we started with, but there's a negative out in front. So it is the opposite of what we started with. So if you can pull out the negative, and it's the opposite of what we started with, then that means it has odd symmetry. Okay? All right, well, you take a look at number 8. Graph it. What are you thinking it could be? Y-axis symmetry. So you think it's the y-axis, which would be even symmetry. Okay, so again, how do we do that? We're going to replace our function with the opposite x, and we're hoping to get the same thing back again. All right, what we start with. So I have the opposite, and then in place of x, we have a negative x being squared. So be careful with that notation. I'm just replacing the x with negative x. All right, going to clean that up. First, we do our exponent. What is negative x quantity squared? Positive x squared, but there's still a negative dangling in front. And then we have the plus 6, and oh, look, that is exactly what I started with. So that equals my original function f of x. So therefore, it is an even function. It's exactly what I started with, therefore it's even. Let's look at number 9. And then that's probably good enough. So if you graph number 9, what are you thinking? Is it even or is it odd? Odd. All right, so we're questioning, is it odd? Either way, I'm still going to plug in my opposite x. So let's say I'm going to take my function and plug in the opposite of x. So using parentheses, negative x cubed minus the negative x being squared minus 2 times, oops, negative x. I love that my pens erase. That's so nice. And then we're going to do the math and sort of clean that up. So negative x quantity cubed is just negative x cubed. First, we do the exponent. Negative x quantity squared becomes positive x squared, but there's a subtract, so cleans up to just the subtracting the x squared. And then at the end, we have negative 2 times the negative x, which would become positive 2x. That is not what I started with. Should I try to take out the negative? So let me take off the negative. Then it becomes x cubed plus x squared minus 2x. Is that what we started with? No. All right, so that does not match. So this is none. It's not even and it's not odd. Okay. Questions for me? Pretty okay? Super. I believe so. I'm not sure.